Hello, my name is Andy Schweitzer, and this is our first of a few videos on stoichiometry. Our first topic is on what's called the stoichiometric ratio. The overall goal here of stoichiometry in general is essentially you are going to be building molecules just like you would build cars, bicycles, hamburgers, grilled cheese sandwiches. Anything you build something, you have a certain amount of building materials. In chemistry, we just call them reactants. And we are going to produce some products. And in every building process, there's a certain quantity of items that are needed to build your product. In chemistry, we use coefficients to describe how many we need. So A plus B, and let's say we need 2 of these and 3 of these to produce 2 of our products. So in any case, these coefficients describe the quantity that we need of A and B. And it will also describe the quantity of C that will be produced. I often describe these coefficients, and you've been balancing chemical reactions since you're probably in middle school. But this is really describing the rate used. It might describe the rate consumed here, or the rate used, and then this is the rate produced. Okay. This whole thing happens in concert, meaning that I cannot consume 3 B's without also consuming 2 A's. I cannot consume 3 B's without also producing 2 C's. Everything happens in concert. These coefficients are often referred to as a stoichiometric ratio between each other, 2 to 3 to 2 ratio. Since the A and the C both have a 2 in front, means that every time I consume 2 of these, I produce 2 of these. So if I produce 10 of these, I would assume that I also consumed 10 of these. That stoichiometric ratio would be between A and C would be a 2 to 2 ratio. I am losing and gaining differently, gaining these and losing this one, but nonetheless 2 to 2 ratio. So our overall goal of stoichiometry is to be able to determine quantities, okay, that we are either going to produce or that we are going to consume. This PowerPoint, or let's say this little video, is really on the basic side where we're not going to get too complicated yet. I'm just going to do a simple example. Let's say, for example, we are going to take the chemical methane. CH4 plus O2 yields carbon dioxide and water. Of course, we balance, and before this chapter, balancing was kind of rudimentary and had no real purpose. But in this case, we will use these coefficients very intently in order to solve problems. 1 carbon, 4 hydrogens. Put a 2 here to give me 4 hydrogens. 2 and 2 is 4 oxygens, and I put a 2 right here. 1, 2, 1, 2. Now, in this case, we are consuming both methane and oxygen together. Missing either one of these two, and the reaction will not run. If I were to give you, let's say, 50 methanes, how many of these oxygens would be needed? Keep in mind, anytime you solve for something on the product side, I would solve for, okay, how many oxygens would I need? Anytime I solve for a reactant, I'm solving for a need, something that is going to be consumed. We need this to build with our 50 methanes. Anytime I solve for something on the product side, it is a produce. Again, here used, need, and here's produce. So I want to know if I consume these guys, how many of these will I need to go with it? Question mark. How many carbon dioxides will I produce? And how many waters will I produce? Without even starting off here with problems, 1, 2, 1, 2, you should note that for every methane you consume, you will need to produce 1 carbon dioxide. Don't let this get too complicated for you, but in a sense, we're just rearranging atoms. And since you have 1 carbon on the reactant side, you only have 1 carbon on the product side. So you can't get more than 1 carbon, 1 here and 1 here. You can't all of a sudden have multiple carbons over here because you only really have 1. Just a rearrangement of atoms. You have 4 hydrogens here, so you have 4 over here. So it's just a rearrangement of atoms. I can't have 1 carbon here and 5 over here. It just doesn't work that way. Can't gain or lose anything just in a rearrangement of atoms. All right, so when I go ahead to solve for these question marks, I will just point out to you that I often use arrows. Okay, I'm going to change my color here just so you can see it a little easier. But when I draw an arrow from here to here, that means I'm using this 1 to 2 stoichiometric ratio. The math is going to be fairly easy at this point, but keep in mind stoichiometry gets more difficult. As I show my math, I'm going to build what's called an ICE table. I-S-E. I stands for initial amounts, and we build this table because things get more complicated. It's nice to be able to have a place to put your information and keep everything straight. But again, from here to here, okay, I'm going to do the math over here, the little math section over here. And the math is very simple as well. For every 1 methane I consume, I need 2 oxygens. So 1 CH4, I'm going to say this 50 CH4s. I have 50 of them. And then I use my stoichiometric ratio. This is a linear relationship. I could use a proportion for this. Get rid of CH4 and go to O2. And for every 1 CH4, I require 2 oxygens. My answer, therefore, is 100. I'm therefore going to say that if I consume 50 of these guys, I will need to consume 100 of these guys. And from here, you can see the math works out quite simple. 1-to-1 ratio. I will show my math here. 50 CH4s at a 1-to-1 ratio means I'll produce 50 CO2s. And again, 50 CH4s at a 1-to-2 ratio of H2O gives me 100 H2Os plus 100 H2Os. In the end, again, we have nothing of this to start with. I don't know how much we have. Some here, I just don't know how much we have. In the end, this is now down to 0. We ran this to what's called completion. Completion means that we essentially ran reactant to 0. That's important for later on in chemistry. But in a sense, it goes completely to products as much as it possibly can until something runs out. This guy, there was some there already, question mark, minus 100 is what would get left over, okay? This would be what I would commonly refer to as the excess, okay? If we had some left over, I mean, if we just had 100 to begin with, then 100 minus 100 would be 0. There would be no excess left over. But in this case, if question mark happened to be bigger than 100, then we would have some left over. And of course, if it was less than 100, then this would run out first, stopping the reaction, and we'd have some CH4 left over. But either way, I would simply have 50 of these guys. This is pretty simple, and 100 of these guys. That is my answer. Okay. There's not much more to it than that. I'm just do maybe one more example of this. Let's try, for example, a different chemical reaction. Let's go with nitrogen triiodide breaks down into nitrogen gas plus iodine gas. These are both diatomic. Decomposition reaction balance-wise, we have 3 here giving me 6 iodines, but 2 here giving me 6 iodines, and my nitrogens are now balanced. Now, in my initial conditions, a stoichromatic ratio, my ending, notice my stoichromatic ratio will always mimic my coefficients. 50, 100, 50, 100, 1, 2, 1, 2. They always mimic. So in this case, all right, I could be given this, but everything is locked together by these coefficients. So I could say, well, what if I want to produce 600 of these guys? How many of these would I need? How many of these would I also produce? And how many of these would I need? Again, on top here, I did this math. I showed my first red arrow as my first calculation, but I didn't show the arrow for the second one. So this very first calculation, let's go with this color. This one was this calculation. Then I did another calculation from here to here. That was this calculation. And then I went from here to here, and that was my final calculation. Keep in mind that the stoichiometric ratio locks everything together. So theoretically, I could have, and very realistically, I could have done an alternate calculation, taking the carbon dioxide produced and jump from here to here. If I produce 50 carbon dioxides, you'd know that for every one of these I produce 2 of these. So I can jump all over the place using these stoichromatic ratios. This would have been 50 CO2s, and at a 1 to 2 ratio equals 100 waters. You should note that for every time you produce a carbon dioxide, you'll get 2 waters. And that matches how many waters I got from the initial amount. So it all comes together. So my bottom problem here, I can easily start, let's just say, from the back side here and say, well, if I produce this much iodine vapor, how much of this would I get produced and how much of this would I need as well? Just by linking together my coefficients. My first calculation will be from here to here. All right, and this is going to be 600 I2s, and get rid of I2 and go to N2. What numbers do I coefficient I use? 3 I2s, 1 N2. 600 divided by 3 is 200 N2s. And therefore, I will lose 600 of this down to 0. I didn't know how, I'm assuming I had none of this before I started, before this thing decomposed to produce it. But I will get, in fact, I'm going to erase this here, this guy here, because I didn't really lose any of this here. I just produced, I started out with nothing, but I will get 600 of these guys. All right, and I'm going to also get 200 of these. And then what about my final initial amount? I'm working backwards here. How much of this stuff would have to have decayed to get 200 of these and 600 of these? All right, well, let's do it. 600 I2s at a 3 to 2 ratio. This is the I2, that's why I have the 3 there. The 2 here is coming from right here. 600 times 2 is 1200. 1200 divided by 3 is 400 and nitrogen triiodides. This, therefore, the original question mark was 400. So I'm going to lose 400 of these guys, gain 200, gain 600. So this would be down to 0, 200, and 600. That is used 2 examples using the stoichiometric ratio and showing the math involved in these linear relationships.